Hello and welcome to this webinar. My name is Henrik Hassel and I'm an associate professor at Lund University at the Division of Risk Management and Societal Safety. And this webinar is produced within the EU project Keyforce. In this webinar, I will present a framework for a risk assessment which is based on using scenarios and scenario thinking. And the underlying rationale for this lecture, well, first of all, risk assessments, as we all know, are performed in a wide range of different contexts. Anything from technical contexts like industrial safety, to more organizational risk assessment, project risk assessment, and so on. And there's a wide range of different methods that are used to perform risk assessments. And based on experience that we have from teaching risk assessment topics and risk assessment methods, we believe that it is important to first learn about the foundations and the principles of risk, the concept of risk and risk assessment, before moving on to the more specific methods and try to be able to learn those methods. We think that this will lead to better quality applications and also an ability to be able to apply new methods in new contexts. So, what is risk then? And this is a topic that has been debated quite significantly in the research literature during the last decades. But still, there is no real consensus concerning what the concept of risk entails. But there are many suggestions, and many of these suggestions have commonalities, and one commonality has to do with the fact that we are trying to look into the future, to foresee different types of events, but we don't know exactly what will happen. So there are uncertainties related to the future state of the system that we are looking at. So this is in the center of all definitions of risk. If there are certainty, if we know the outcome, there is no risk. And on this slide, I've listed a number of common definitions of risk that you sometimes find in the literature. The first one is perhaps the most common one, where risk is seen as the combination of probability and severity of adverse effects. So it's a two-dimensional concept, basically, where we try to foresee different possible events with their negative effects, and we estimate the probability related to those events. A very closely related concept or definition is that risk is the uncertainty and severity of negative consequences. The big difference between these two definitions is that here we talk about uncertainty, which is a broader concept compared to probability. Probability is a very narrowly defined concept, but uncertainty opens up for other possibilities to describe this uncertainty, not only probability concept. The third definition is that risk is the possibility that human actions or events lead to consequences that affect what humans value. And what is significant for this definition is that the last part, it's the fact that what is a negative consequence has to do with human values. It's up for a subjective choice. We might value different things. So something is a consequence only if it affects human values. The fourth is also very common, but much more narrow than the first three, where risk equals expected loss. In this case, an analyst would be forced to consider rare events that give rise to very large consequences compared to quite frequent events that give rise to quite small consequences. These would be equal in severity if the expected value is the same. So this sort of forces the analyst to
to view those two types of events as equally severe, which is not always in accordance to the preferences of decision makers or people in general. And the final definition of risk here that is often used especially in the disaster risk management area, is that risk is the combination of a hazard, for example, an hurricane or an earthquake, and the vulnerability of the society, for example, or a people or a person with respect to this hazard. So the combination of those two give rise to a risk.
So the definition of risk that is used as a basis for the framework that I will present in this lecture is what we think is a quite pragmatic definition. It's very common in the field of safety, nuclear safety, technical safety, industrial safety, areas such as those. And in this definition, risk is the answer to three different questions. And the questions are: what can happen or what can go wrong in the future concerning a system? How likely is it, and what will the consequences be? And basically, if you can answer these three questions, then you performed the risk assessment, risk analysis. So this is what we can call a scenario-based definition, because the goal of a risk analysis is to try to map out the different scenarios that can occur in the future and estimate the likelihood and the consequences of these scenarios. And this definition is based on a number of references that can be seen in the slide here. So the framework for risk assessment that will be presented now is composed by a number of different phases of stages, 6 in total. So the framework should be read from bottom up. So we start with laying the foundation for risk assessment by addressing values and objectives, and then we move upwards. And I will describe each of these steps in the coming slides. The first 4 phases here can be said to be part of the risk analysis, and if you also include presenting and evaluating risk, it constitutes the risk assessment. And this is, for example, according to the language that is common in the field of risk assessment. For example, if you look at the ISO standard. In the first part of the framework, we address values and objectives. The question we are asking in this phase of the risk assessment is: what is worth protecting? What is worth achieving in the context where we are doing the risk assessment? And this is very dependent on the perspective or the preferences that we have. So it's a subjective choice. So just to give an example of what we mean by this is, let's say you're doing a risk assessment in the context of a city or a municipality, and it is exposed to natural hazards. So the question, what is valuable and important to protect, is a subjective choice. Often it entails the life and health of citizens or visitors, or people working in the city and municipality, but it can also include the functionality of the critical societal functions to protect the power distribution, to protect the water distribution, and so on. It can also concern environmental conditions, to protect cultural values, economic values, and so on. So this is a choice that the analyst has to do. And of course, this choice has a major influence on how you outline, how you perform the risk analysis. If you include environmental values, then of course you need to maybe use some environmental modeling. If you only look at life and health of the citizens, then you need some models that can calculate the consequences for life and health of the citizens. So this really puts the basis for the risk assessment, and therefore it should be specified at a very early stage in the risk assessment. the problem is that this is often not done in practice, but rather it is assumed that everyone agrees on the values and objectives, which is not always the case. So the next step of the risk assessment framework is the context and system description. So the context and system description has to do with describing the system, what it includes, what it does not include, the limitations and so on. And this is extremely important because it provides the baseline for the assessment and also for being able to communicate the result from the assessment. And system descriptions may focus on many different aspects and perspectives. It can include a focus on the technical part of the system, the organizational aspects, the human, the social aspect, and so on. And typically, there need to be a lot of different competencies represented when developing the system description, because it is here that the common understanding of the system and its context is developed. There are many different ways to describe the system. It's common to use structural models or functional models, and often a combination of both structural and functional models. So a structural model would be, for example, the top drawing here, which is basically just a description of the different components, the physical components, and and how they fit together. A map or a sketch would be common ways to describe the system in a structured way. A functional description is has more to do with what is happening in the system. For example, what is the normal sort of procedures and phases that are performed in the system. So it could be a description of a project plan or a procedure. So the third step of the framework is where we start to answer the first question of the definition of risk that we presented a few slides ago. We are starting to talk about risk scenarios. A risk scenario is something that happens in the system in the future, or it may happen in the future. It's a sequence of events. And the goal of a risk assessment is to describe all the different risk scenarios that can happen and those that lead to negative consequences. Typically, it is that type of scenarios that is of interest in a risk assessment. Although there are also risk assessments that look at positive outcomes, positive scenarios. But for example, in the area of safety, then it is typically the negative consequences that are of interest. A good starting point is to describe what is sometimes called as planned or success scenario, the S0 scenario. And this scenario is a description when everything in the system evolves or develops according to the plan, according to what could be characterized as the successful scenario. And this is a very good starting point to identify the risk scenarios, because identification of risk scenarios has to do with identifying the deviations from this success scenario. So how can a negative sequence of events occur that takes the state of the system away from the as planned state? So an example of a success scenario in the context of a chemical process industry, it could be something like this. And now we also illustrate the development of the scenario using a state space diagram, which is basically displaying a state change over time. So a line in the state space is a scenario. So there's a time axis running along the line in this diagram. So the success scenario in this example could, for example, be first that some raw material is fed into the reactor. There's a stirring and heating of the mixture. There's a reaction.
There's a separation of the new products that are created in this reaction, and there's a cooling. So in this case, it's 5 different phases of this success scenario. So the next question that we ask ourselves is, well, how can negative events occur here that takes the system state away from the success scenario into some fail state? So risk scenario has always some type of initiation and some type of ending, and it starts with an initiating event. That's the concept that is typically used, and this is quite often triggered by a hazard. It could be an external hazard, like a flood occurs that affects a municipality or an industry or something. It could also be some internal failure of a technical component, or the fact that wrong input material is fed into this reactor, and so on. But something happens that that initiates an event sequence that constitutes the risk scenario. So, for example, if we go back to the success scenario of a chemical process plant, we have some feed-in of raw material, there's some stirring and heating, there's a reaction, but here we might have an initiating event. Let's say we have a rupture of the tank. It might be due to an external, someone is running into the tank, or it could be corrosion or something that makes the tank rupture, maybe too high pressure or something. And then this event sequence goes on until we end an end state. And an end state is reached where it's possible to estimate the negative consequences. So how much of the value basis is damaged. It could be in terms of a fatality or an economic loss or something like that.
All risk scenarios have to have some initiation and some ending. And the common language to use is that a risk scenario always starts with an initiating event. And this is often triggered by a hazard of some type, which could be an external hazard, like a flood is occurring or an earthquake is occurring, or it could be some internal aspect of the system, like a technical failure of a component, or that the wrong input material is fed into a reactor. But the initiating event is where the state of the system is departing from this success scenario, the S0 scenario. So just to give an example, if we go back to the example we had, the success scenario, we start with feeding in raw material to the reactor. Still everything is according to the plan. We stir and heat the mixture. There is a reaction, but then we might have an initiating event, which could be a rupture of the tank or of the reactor. Which could be caused by either some external stressor, it could be too high pressure, it could be corrosion of the walls of the tank, or so on. And then this also has to have an ending. So the initiating event gives rise to the risk scenario that ends in an end state. And the end state, when you reach the end state, it should be possible to estimate the negative consequences of the risk scenario. So for example, if the value basis is human life and health, it should be possible to estimate how many fatalities will arise. Or if the focus is on economic losses, what is the magnitude of the economic losses? So the scenario needs to be described in such a detail that so that it's possible to estimate this.
Another aspect of the risk scenarios is that each initiating event can always lead to a number of different risk scenarios. It's not just one initiating event that leads to one end state. There's branching. And this branching can be structured using, for example, an event tree that you can see in the top right corner here. And this is similar to a decision tree, for those who are familiar with that. And how these risk scenarios evolves over time is determined by different conditions in the branching points. So for example, typically, at least the technical system has many different barriers, and these barriers might function or not. So if the barrier functions, then you have one scenario. If it does not function, then you have another scenario. So that's why you have the branching. So for example, does the flood protection barrier function or not? Or does the early warning system function or not? So the branching basically represents our uncertainty about what will happen in the future. So it can also be what is the timing of the initiating event? Does it occur during night or during day, during summer, during winter? So it has to do with variability or natural variability or stochastic uncertainty that we want to be able to map out, because it leads to different magnitudes, severities of the consequences. So this then leads to the question, how many risk scenarios can there be? And in theory, the number of risk scenarios, you can say that they approach infinity. There are an infinitive number of sort of possible branching. And this we can illustrate by using the space of risk scenarios. So what you can see here to the right is it's just an illustration of the different possible risk scenarios that can occur in the future. So just to give you a few examples, let's say one possible risk scenario could be a pipe leak of a particular diameter or a particular area, or a particular size, occurring at a particular time. And it could be the same leak but occurring at a slightly different time. It could be a tank rupture of a bigger size occurring in the evening or during day, and so on. So each of the different risk scenarios that can occur can be illustrated by just a point in this diagram. And obviously in this diagram we could plot out an infinite number of points, because in theory you can describe a risk scenario with basically with an infinite level of detail, going very much into the details. So in theory it can look something like this, and of course in practice it is impossible to describe all these risk scenarios in detail, because you don't have time and resources to do it. So you need to be pragmatic and find a finite set of scenarios that can represent everything that may happen in the future. So rather than describing scenarios in detail as the different dots, you have to describe scenarios using scenario clusters or categories. For example, you have one scenario that is a small pipe leak, you have a large tank rupture, you have a large pipe leak, you have a medium gas cloud explosion, and so on. So you try to, with a number of representative scenarios, you try to cover everything that can occur in the future. So when describing risk scenarios, the risk analyst has a number of different goals or objectives. 4 of them are especially important. The first one is that the level of detail should be suitable. The second one is that the risk scenarios that are included should be complete. The third one is that the scenario should be disjoint or non-overlapping. And the final one is that the risk level should not be over or underestimated. So each of these 4 will be described in the coming slides. So the first objective when you describe risk scenarios is that they should have a suitable level of detail. So one rule of thumb that you can use is that the detail should be enough so you can make sufficiently accurate consequence estimations. So what do we mean by that? Well, if we take the example of a flooding again, and you have an initiating event where you have a 50 centimeter flooding, it is likely that only this information is not detailed enough to allow for sufficiently accurate consequence estimations, because a 50 centimeter flood can give rise to large consequences. For example, if the protection, the barriers that are in place is not successful, if it occurs during a maybe the flooding has a quick speed of onset and it occurs during nighttime, then you have very large consequences. But if protection works and so on, you have small consequences. So the variation in the consequences are very large. So that's why you probably need some type of subdivision of this scenario in order to make the consequence estimations more accurate. So for example, we could subdivide it into two sub-scenarios, one where the water treatment plant can be successfully protected, and one where it's not successfully protected. That would of course lead to larger consequences, because you might have a problem with the water distribution. Then maybe you need to subdivide it even more, because evacuation of a city depends on if the bridge can be used, if it's protected successfully or not. So maybe now it's possible to estimate the consequences with sufficient accuracy. At the same time, we could of course continue to subdivide these scenarios in even further details, but they have to be manageable. We have to be able to treat the scenarios with the available resources, because in the next step, of course, we want to estimate the probabilities and the consequences, and having too many scenarios will not, then it will not be possible to do that. So sometimes you have to go in the opposite direction. Maybe you have a number of very detailed scenarios and you need to cluster them because they have some similarities. That means they can be treated together. The third objective when describing risk scenarios is that the scenarios that are included in the risk assessment should be non-overlapping. So if you have scenarios that overlap or are not mutually exclusive, they may lead to double counting when you aggregate the scenarios. So just to give you an example concerning earthquake risk scenarios, an appropriate scenario division is, for example, the one to the left. You might have three scenarios: one small earthquake with a Richter magnitude smaller or equal to 4, one medium size, it's between 4 and 7, and one large one is above, greater or equal to 7. So these are mutually exclusive. An event that happens in reality will be classified as either or, either one of these scenarios. It cannot be in both at the same time. If you look to the right, you have an inappropriate scenario division because you have an overlap between the first and the second one. For example, a Richter scale of 4.5 would be in both categories. And you also have an overlap between the second and the third scenario, because a Richter scale of 6.5 would be in both categories. And this would be problematic if you want to calculate, for example, an aggregated likelihood, because then you would exaggerate the likelihood of the different risk scenarios. So the next step of the risk assessment framework is the likelihood and consequence estimation. So starting with the likelihood estimation, this is of course the second question of the risk definition. So once you have mapped out and described the different risk scenarios, you want to estimate how likely they are. And here you can use a number of different scales or measurements to measure the likelihoods. You can use a rather simple ranking scale, a qualitative ranking scale, where you have defined a number of different categories, 1 to 5, and you classify each scenario in one of these different categories, ranging from extremely unlikely to very likely, for example. You could have a semi-quantitative ranking scale, where you again have these, it could be 4, it could be any number of categories. The difference here is that now you also have some quantitative estimation, or it could be an interval that with unlikely we mean 1 per 10 year to 1 per 100 year. So this is to become a bit more specific, a bit more precise, because if you only use words to describe a likelihood, then different people can interpret these words in different ways, and they have different meaning in different contexts. So typically it's preferred that some type of quantitative measure is also used. And you can also go fully quantitative, which you are doing in a quantitative or probabilistic risk assessment, where you use frequencies or probabilities to estimate likelihoods. Frequencies, it could be number of events during per time unit, and probability, of course, is something between 0 and 1. For example, the probability that the water sprinkler system will be successful given that there is a fire. And which of these types of scales you should use depends on the context. Quite often it's preferred that we use quantitative measures because they are a bit more precise, but it also requires that the data you're using is a bit of more higher quality. So the estimations that are performed, they can be based on a number of different information sources. Typically you want to base it on the historical data, the statistics, but in many cases the statistical data, historical data is rare, or it's not relevant because since you are doing the risk assessment looking into the future, the conditions might be different than they were in the past. So typically these are not sufficient, and therefore you can use logical models and also expert judgment to actually estimate the likelihood. And what is important to think about when you are making estimations of likelihood is that if you have a cluster of scenarios, for example, you have described a flooding scenario, and the flooding, the water levels could be between 2 and 4 meters higher than normal, then the likelihood has to be estimated in total for the cluster of scenarios, not for an average likelihood or something like that. It's the total likelihood, otherwise you will underestimate the likelihood. The next step of the framework is the consequence estimation. And the consequence estimation has a direct relation to the first step of the framework, which was the value basis. Because when you estimate the consequences, you want to estimate the extent of the damage on the value basis. For example, if the value basis has to do with life and health of citizens, then in this phase you want to estimate, for example, number of fatalities or number of injuries. And similar to the likelihood estimation, you can use qualitative ranking scales, you can use semi-quantitative scales, or you can use quantitative scales. So the options are the same when it comes to the consequence estimations. Typically you can use simulation models, calculation tools, expert judgments, and historical data to estimate the consequences of different risk scenarios. So for example, if you are doing a risk assessment for fire case, you typically use fire and smoke simulation tools, you use egress tools. In the case of a process plant, you maybe use some gas dispersion models, you use some effect models on how human beings are affected by inhalation of toxic gases and so on. When you estimate the consequences for a scenario cluster, similar to what we talked about when it comes to likelihood estimations, it is important to think about that you need to estimate the average consequences of the cluster. So for example, if you have again the flooding of between 2 and 4 meter, then of course the consequences for a 4 meter level is higher than a 2 meter water level. But the consequence estimations here should be then for for example, for 3-meter flood, because that's in between, it's the average consequences. And that is because you don't want to overestimate or you don't want to underestimate the level of risk. You want to have an as precise estimation as possible of the total level of risk. If it would be the case that the difference, the variation between 2 and 4 meter water level is too high, then you would subdivide it into more risk scenarios that you can make a more accurate consequence estimation of. So this brings us to the very end of the framework, and that has to do with presenting and evaluating risk. So after conducting the first 4 phases or stages of the risk assessment, you probably end up with something looking like this, where you have a number of different scenarios. In a big risk assessment, you probably have a large number of risk scenarios. You have a likelihood, you have consequences for each of these scenarios. And the problem with this is that the information is quite a lot of different information. And it's difficult to use this information directly to inform a decision. So you need to do something with this information, present it in a way that facilitates the understanding and also makes it possible to evaluate the risk. And there are many, many different ways to present risk. You can use some point value or some index. It's very common that you, for example, use an expected value where you multiply the likelihood and the consequences for each of the scenario and then sum the product across all the different scenarios. You would get an expected value. Expected number or average number of fatalities per year is, for example, an expected value. Of course, what you do here is that you compress a lot of information into one single number, so you also lose some information. You might use a matrix where you plot the different scenarios, and then you would see, well, which of the scenarios are associated with high risk, which would be both likelihoods and high likelihoods and high consequences. You might use some graphs. In this case, this is called an FN curve, where you get information about both the likelihood and the consequences of different scenarios. So that would be much more information than expected values, for example, but also a bit more difficult to interpret the information. You can use maps if you have risk that is related to some geography. Then you can show that on different maps to see where do we have any hotspots, do we have any areas with very high risks that should be targeted for risk reductions, for example. And of course there are many other ways to do it as well. You can also focus on trying to illustrate or present what are the major risk contributors, and you can also present uncertainties. Because these are also information that can affect decisions and how, for example, you should target the system with risk reductions. So, looking at the risk evaluation stage, if we look at the first part of the risk assessment framework that has to do with the risk analysis, that is concerned with trying to obtain an as well-informed estimate of the risk level as possible, to use the best available knowledge to understand, well, how often do we get negative consequences and how severe are these negative consequences. The risk evaluation, on the other hand, has to do with determining whether the risk level is acceptable or tolerable, or whether we should do something to reduce or control the risk. And again, quite often the different ways of presenting risk is also connected to different ways of evaluating risk. If you have risk levels expressed for human individuals, for example, then you might compare it with some criteria, some acceptance criteria that we should not be allowed to expose an individual to higher risk levels than a particular value. that would be a rights-based type of criteria. There are also utility-based type of criteria when it comes to risk evaluation, where you weigh the pros and cons of a risk or a risk reduction measure to come to a decision whether a risk or should be accepted, or whether a risk reduction measure should be implemented.
We have now come to the end of this brief webinar on the topic of risk assessment. And this has been a very brief introduction to this topic. Hopefully this has sparked some interests in the topic and the challenges and principles of risk assessment. The underlying idea of and the underlying rationale of the lecture has been that we think that learning the basic principles of the concept of risk and performing risk assessments, that has to come before learning the specific methods of risk assessment. We're presented a framework for risk assessment that is general in the sense that we believe that it can be used in a wide range of different contexts, in different disciplines, to focus on different types of systems and different types of negative effects and so on. And this framework can be used to provide a common language, common foundation for performance of risk assessments. And obviously there are much more to say about risk assessment, how to conduct risk assessment with high quality. So this has only been touching upon a few of the important topics. I would like to thank you for your attention, and if you have any interests in learning more about risk assessment, please get in contact with me, and I will try to provide some additional for example, advice on literature and things like that. Thank you very much. Goodbye.